get the session recording going. Also, welcome Alicia. How's it going? Let's go ahead and let's start talking about physics. So yesterday during class we were talking about especially kinematics and one-dimensional kinematic motion. So can either of you sort of explain to me what exactly is the difference between velocity and acceleration?
I still get kind of confused by that. I thought velocity was like it's a force in a particular direction.
Is it a force?
Not a force, but yeah, I'm having trouble here. Yeah, there's a reason why I'm here.
Yeah. Go ahead, Alicia.
Oh, for velocity, would it like well, I guess just by like the units, it would just be like the distance it travels for a certain time, right? But then like acceleration would be how that changes over time.
Mm-hmm. Exactly. So how is velocity different from speed? Because speed is something I would assume most people can sort of conceptually grasp. You're in a car, it's driving 60 miles an hour on the highway, that's your speed. How is velocity different from that?
I have no idea.
Oh, velocity or acceleration?
Velocity.
Oh, velocity. I think he said that speed was magnitude, right? And so velocity would just be like with a plus or minus.
Not not necessarily just plus or minus, but in one-dimensional motion that would be the case. But more specifically, more generally, actually, don't make me pull out the Despicable Me quote.
Would it be like with the velocity is speed but with direction?
Exactly. Direction and magnitude.
Oh.
Oh, yeah. It's been so long since I've seen that movie, but I still remember that quote. But, so, velocity, so obviously we have our speed, which, if we're in a car, let's pretend this is a car. Boom. We have our little triangle. That's our car, and it's moving at, let's say, 60 miles an hour. The velocity is specifically, it's the 60 miles per hour. The speed is the magnitude of the velocity, but we also denote some sort of direction. In this case, let's call it the x direction. So the velocity, and we'll denote it with a little vector. Because I know, and then like for speed, it's usually v, and then we have the little magnitude bars. Our velocity is going to be plus 60, and then we'll call that in the x direction. Or we can just call it plus 60 if we're talking about one dimension. Now, what about if the car is traveling in the opposite direction? Would it have a positive or negative velocity?
It would be a negative velocity, right?
And so would its speed be negative?
Well, its speed's not negative, but
Exactly. Yeah. So we can have a negative velocity is traveling in the opposite direction, in the negative x direction, but it still has a positive speed magnitude. And so what is acceleration then? So you mentioned it was a change in velocity. Alicia, could you elaborate that a little bit?
From the videos, like for when we're doing the charts for velocity and then acceleration, uh, the acceleration is always like the slope of the what's it called, of the velocity graph.
Mm-hmm.
So it would just be like, for example, like if the velocity was getting smaller, then it would be a negative acceleration.
Mm-hmm.
And then vice versa, like if the object was going faster and faster, then it would be a positive acceleration.
Yep, exactly. Now, what if we had a car that was going in the negative x direction, so it's traveling to the left, and it's speeding up? Would its acceleration be positive or negative?
Negative?
Yep, it would be negative. Because
Can you explain that?
Lucia, you want to explain? Why is it negative?
Yes. Yeah.
Oh, because, thinking about it mathematically, like, if we had, like, a negative velocity, like -6 or something, if, like, we were multiplying the amount of seconds that the object is going at by the acceleration to get its velocity, then in order for, like, if it was going to the negative sign, then the velocity you would get from the acceleration would also be negative. And that would just make the velocity bigger.
Or the magnitude of the velocity bigger. So the speed gets bigger, it's traveling in the negative direction. The way I like to think about it is the acceleration is negative because the velocity is becoming more negative. So if we graph our velocity, let's say we start here and it's going down like that, it starts negative and it's becoming more negative. The slope of the graph is negative, right? If we take the derivative, it's going to be some negative value. So in that case, in that definition, the acceleration would be negative.
And to reiterate, he said yesterday if the velocity and the acceleration are the same sign, then it's considered like speeding up, correct?
Exactly.
Okay. Just want to make sure.
And if they're opposite, obviously we're slowing down. So we can actually have a positive acceleration, but be slowing down if we're traveling in the negative direction. Does that make sense?
I mean, conceptually that screws me up, but
I don't blame you.
Guess.
I don't blame you at all. Nothing in the realm of physics really is able to be understood conceptually. I'll put a little asterisk by 99% of people. There's a weird 1% of people that somehow their brains work differently. I'm talking about this one guy in my physics class, is Bobby. Everything made conceptual sense to him, and no one else in all my when I was taking quantum mechanics last year, everything made sense to him. No one else understood what was going on conceptually. And the same thing happens for you guys, even in these 100 level classes. Nothing is really going to make sense conceptually. But you're still able to understand it if you have faith in the math. If you worship your equation sheet and really, take your time with every problem and make sure your math checks out, you'll get the right answer most of the time. You might get all messed up with positive and negative signs, and conceptually you'll be like, oh God, what's going on? But you'll get used to doing that. You'll get used to that. I'm assuming you guys probably aren't physics majors, but
no.
What's your major?
Computer science.
Computer science?
Mine's biochem.
Biochem? Yeah. So, I guess I'm trying to draw a parallel, because I tell this to a lot of freshman physics majors and also like engineering majors. A lot of what you're going to do isn't going to make much conceptual sense, but the math checks out. So get used to being uncomfortable. And the same thing can be said for, I guess, especially for biochem. Especially, I assume you have to take orgo, right?
Yeah, that's done with.
Oh, you've already taken orgo?
Yeah, it was interesting fun.
I was gonna say a lot of what you're doing in orgo doesn't. Would you say it makes much sense? Like you sort of memorize things and you at least somewhat understand what's going on, but do you truly know why? you just put your faith in what you memorize, right? Or at least in what you learn.
Yeah, sometimes our professor just say it happens because of magic. Just 'cause
Exactly. Well, I'll tell you, that magic is quantum mechanics, which I'm not even going to get into. But it's sort of the same case here, where in this case, you're not trusting in it because of magic, you're trusting in your answers in this class because of math, which I suppose to some people is magic. I guess to summarize, get comfortable being uncomfortable and
Right.
worship the formula sheet. Because if something makes sense, if the math makes sense, it's probably right. So, let's go ahead and hop into an example problem. We're going to go ahead and have a car. We're going to once again have our triangular car. And we're going to start it at rest. Let me go ahead and actually move it over slightly. We're going to have it start at rest at the origin. We're going to label this as x equals 0. X, not lambda. So we're going to initially accelerate forward, constant acceleration of 3 meters per second squared for 5 seconds. And then we're going to travel at constant speed, whatever the speed at the end of the 5 seconds is, for another 2 seconds. And then we're going to brake hard and come to a stop in a single second. And then the car is going to accelerate back towards the origin at 2 meters per second squared for 2 seconds. So there's a lot going on here, but as long as you break it down step by step, you should be able to understand what's going on. So let's go ahead and sketch the displacement, velocity, and acceleration versus time graphs for this 10 seconds. Let's take 5 minutes and we'll go over it. I recommend starting with acceleration and working your way back to displacement. All right, let's go ahead and talk through this problem here. So we want to go ahead and understand what our acceleration, velocity, and displacement versus time graphs are going to look like so that we can more accurately understand how this motion is actually going to look. So do either of you want to start out? What would the acceleration versus time graph for this movement look like?
It would have a gradual slope just going upwards.
Would the acceleration versus time graph have a slope?
Not. I guess not. See, I guess that's why I'm having trouble with this, because I don't quite understand how to graph them correctly too. Because our acceleration is 0, right? And when we first start.
Is it 0 when we initially start?
I guess not. So it would start at 3 then.
Mm-hmm.
Right?
Exactly. So it's going to start.
Or,
it initially accelerates forward with constant acceleration. So it's going to start at 3. What's it going to look like?
It's just gonna go straight, right? Oh, I guess it's accelerating, so it is. Yeah, I don't know.
It's a constant acceleration, right?
Yeah.
So it would not just be a straight line like this? Straight?
So no, it would be going upwards.
What's the difference between velocity and acceleration? You're thinking about velocity right now, I think.
I honestly, I can't remember.
You're getting them mixed in. Alicia, you want to come in and help him?
I got a little bit confused with this one too, but yeah, for the first part, I also had a straight line just because, well, when it's constant acceleration, it doesn't change. Sort of. But then at 5, I dropped down to 0 because it says it travels at constant speed.
Exactly. Let me actually, give me just a moment. Let's see, am I able to... No. Whatever. I'm gonna redraw them with red lines here. So that then, so we have our initial 5 seconds. It's a constant 3 meters per second. And then you said it drops down to 0?
Yes, I think. Just because it says it goes at constant speed, so that would mean that it doesn't have, like its slope would be 0.
Exactly. So it's going to be traveling at a constant speed, so the slope of the velocity graph would be 0, so the acceleration is 0. And we're going to have just a, like, I'm going to draw a little dotted line here to sort of indicate that it's like a step function. It instantly goes from 3 to 0. So now what's going to happen? What happens next?
Point, I got kind of confused because then it says it brakes hard and comes to stop for 1 second. And in my mind, that would mean that, like, it's, like, decelerating. Or I guess the video said not to use, like, it's gonna slow down a lot. So maybe it would have, like, a negative acceleration.
Mm-hmm. That's exactly right. And it's going to be a relatively large value. We'll do something like that. And we'll have another dotted line here. Going to have a relatively large value. And this isn't going to be exactly to scale. And so then, what's going to happen? It's going to accelerate backwards towards the origin at 2 meters per second squared for 2 seconds.
Just a straight line below 3 meters per second.
So it's going to be... So is it going to be right here?
Yeah. I mean, moved over a little bit. I don't know.
Oh, you mean like this?
Yeah. Or is that not right?
Is this right?
I don't know.
But I had to.
Well, I'll give you a hint. It's not right. So if I tell you it's not right, what is it? What is going on? I'll give you a hint. We're somewhere out here, right? We have driven our car, sped up, constant, and then brake right here. And then we're going to start accelerating back towards the origin for 2 seconds.
So is that it's not negative acceleration, is it?
Why wouldn't it be?
I don't know.
Explain yourself, sir.
Yeah, I'm not entirely sure.
What if I told you it was a negative acceleration? Rationalize it. Explain why would it be negative? Well, we're starting at, for this little part here, we're starting at rest, right? At this point in time, we're at 0 velocity. We're at rest. And then we're going to start moving backwards, back towards the origin in the negative direction, right?
Yeah, hold on.
So it would have to be a negative acceleration here.
Just out of curiosity, for like the acceleration time graphs, Are we ever gonna use like slopes? Slope? Because I know
Um,
he said a straight line, but I wasn't sure if that just meant like we're not gonna get like parabolas or something like that.
I, off the top of my head, I am not sure. I'm pretty sure you won't see any examples with changing acceleration in this class. I'm pretty sure it's pretty much all constant acceleration because changing acceleration gets real ugly. And I know because it's been 5 years since I actually covered this material myself. But when I took classical mechanics, which is essentially the upper level physics major equivalent of this class for that we take like in our third or fourth year, we did a lot. We did some changing acceleration examples due to like changing mass and air friction, air resistance, and it got really ugly really fast. So I'm pretty sure you don't actually have any examples where acceleration is changing. Like it's any accelerations you'll see are going to be constant for a second, and then it'll instantly change. It'll instantly change. It'll instantly change to something else.
I see.
But so I'm like 95% confident in that. Maybe I apologize if you see on a quiz this next week that a changing acceleration, but I'm pretty sure you won't. So now that we have our acceleration time graph, let me actually go ahead and label that. We have our acceleration. Let me draw that a little nicer. Acceleration versus time. What would our velocity versus time graph look like? How?
From the or-
Go ahead.
from like the origin to like 5, it would just be steadily growing, like with a positive slope.
Exactly. We're going to be initially... Oh, crap. Boom. So we're going to start, and where are we starting? Are we starting at 0, or are we starting at an initial velocity?
I think at 0.
And why is that?
It says that it starts at rest.
Exactly. Starts at rest. So you said we are going to start at 0, and it's just a straight line increasing for the first 5 seconds. Something like that. So then what happens?
And then just another 2 seconds of a straight line.
A straight horizontal line?
Yes. Yes?
Yeah,
I
you're
don't
right.
know.
Yeah, it's going to just look something like this. Maybe a little bit shorter than that. Boom. So we're going to have our 2 seconds of a straight line, constant velocity. So then, what happens?
We break for a second, but
It's going to essentially go from this point here very quickly down to 0, right? In just 1 second. So then what happens?
and then just accelerating back towards the origin.
Exactly. So what would that look like?
I want to say just another positive slope line coming from our last line, but
So
I feel
like
that's
this?
wrong. Yeah.
You're close.
So when they mention origin, would that change anything here?
Well, the car accelerates back towards the origin.
Yeah. So like it would have a wouldn't be negative?
Why wouldn't it be?
I don't know. These things always confuse me. I can't wrap my head around whether.
I'll give you a hint. This graph here that we've created would be accurate if we were talking about speed, not velocity.
Okay.
But what happens instead of... So obviously for the last 2 seconds, our speed is increasing 2 meters per second squared for 2 seconds. But we're not going further out, right? We're not continuing to travel in the positive direction. We're going back towards the origin. So it's in the negative direction, right? So
yes,
all we have to do is do that.
Okay.
It's a slope. It's a gradual negative slope in the negative direction where our velocity, our speed is increasing. Our velocity is becoming more negative. Does that make sense?
Yes.
So we're going to say velocity and time. Also give our acceleration a little vector notation thing. This T is wide as hell. So now, what would our displacement versus time graph look like?
Would it be like kind of like a trapezoid?
Would it be?
That's what I have.
Would it be a trapezoid, or? So, first of all, there's one part of this motion that's going to be very simple to draw on a displacement versus time graph. Which part is it?
Going back to the origin. I don't know what you're trying to ask.
Well, what did you say, Alicia?
Right. Like when it stops, it would just be like a straight line in the position time graph.
Not quite when we stop. Let's think of it this way. When we went from acceleration to velocity, our flat lines here became straight lines, right? So where a positive flat line became a positively sloped line, a negative flat line became a negatively sloped line, and our zero value here became a flat line at a certain value. And so that we were going from acceleration to velocity, we were essentially doing an antiderivative. And so if we do another antiderivative to go from velocity to displacement, which part of the velocity time graph would be a straight line?
It would be the constant speed for that 2 seconds.
Exactly. It's this second part here with the constant speed. And what would that look like on a displacement time graph?
Just I want to say a flat line, but I don't think that's right.
It's not going to be a flat line. Well,
Yeah,
a flat line would mean it's not moving.
Okay, yeah.
Positive or negative sloped?
Positive.
Positive?
Exactly. It's going to start at whatever initial value, and it's going to increase. Imagine that's a straight line. But it's going to look something like that on a displacement time graph. These other sections of the graph aren't going to quite look like that. Do you guys know what they do look like?
No.
Do you guys know what the antiderivative of a straight sloped line is?
Yeah, just some first order degree polynomial. Right?
Is it first order?
First degree, right? And if it was 2, then it would be like x. 2x plus c, whatever.
isn't that what this is here? This is 3x.
Like a curve.
All right, Alicia, repeat. You're like cutting out.
Oh, it'd be like a curve.
It'd be some sort of a curve, exactly.
Okay.
And you mentioned something about polynomials. You know what specific type of polynomial?
No. That's not a first order?
Well, first order would be the straight line, right?
Gotcha. Oh, yeah, second order. Duh.
Second order, exactly.
Yeah.
It's going to be a parabola.
Yeah.
It's going to be a parabola where, let's go ahead and actually, let's go ahead and create our axes. This here, boom, black. We're doing here. And because we're all working in the positive direction, we don't need to worry about having space on the negative axis. There we go. Oh, damn it. Okay, so it's going to be a parabola where we are starting out at 0 velocity, which means we're starting out essentially as a flat line. And we are going to parabolically increase up to a certain point. And that actually stayed flat a little longer than I wanted. It looks something like that. It's going to be like a parabola where it slowly increases up to a certain point. And then we said our constant speed section is going to just be a straight increasing line, right?
Mm-hmm.
It's going to look something like that. Right?
Yeah.
And so what about our braking section? What is that going to look like on our displacement time graph?
Isn't that like, again, like a parabolic curve going towards the x or the time axis?
Is it going to be going down? Like that?
Oh wait, no, it's still going forward.
Mm-hmm. Alicia, you want to say something?
It wouldn't move, right? So the t would change, but x wouldn't.
Well, once we were braked, but we still have this section where we still have a positive velocity. It's just decreasing down to 0. So we're going to end with some sort of we're going to end with a flat line. And like Sam said, it's going to be another parabolic curve. It's going to look something like that. We're going to, I can actually make that a bit smoother. It's going to look something like that, where we're starting at our initial speed from before, and we are braking to 0 speed, where the slope of our line is 0. So then, what does our motion look like for our last 2 seconds?
Accelerating back towards the origin.
Yep, exactly. So, is that a straight line back towards the origin?
No, it would be some gradual curved line.
Yep, exactly. It's going to be another parabolic curve, and it's going to be a slower curve than
what we started with.
Yep.
3 meters per second.
It's going to look something like that. I don't know. You get the gist. Maybe not quite to scale, but it's going to look something like that. That's our displacement versus time graph.
So with the acceleration graph, is it always done in those, not piecewise, what did you call them? Like,
Step function?
The steps. Yeah.
Yeah.
Is it always going to be like that?
Pretty much always.
At least within this class.
Yeah, within this class, that's pretty much all you're going to see. Because as I said before, changing acceleration examples get real funky real quick.
Yeah. Okay.
So now, just a few quick rapid fire questions. Since we have our graphs now, we sort of can more completely understand what our motion looks like. What is the speed of the car at t is equal to 4 seconds? Do either of you know how to get the speed of the car at t is equal to 4 seconds?
I'm trying to think. That's the. No, it's not that. I don't need an equation for this. I would just have to look at the graph, right?
I mean, you could look at the graph, but we haven't drawn any values on here.
Yeah, that's what I thought. Okay. The speed.
We use like the v equals v naught plus at equation.
Mm-hmm. V is equal to v naught plus at. What is v naught?
0.
0. What is our acceleration?
3.
3 meters per second squared. What is our time?
4 seconds.
4 seconds. What's our final velocity? What is our instantaneous speed of our car at t is equal to 4 seconds?
12 meters a second.
12 meters per second. Exactly. So we have, let me go ahead and organize this real quick. We have A and B, 12 meters per second. And then what would be the acceleration of the hard brake between t equals 7 and 8 seconds? What would the value of this acceleration be? There's a few equations you'd be able to use for this.
What was the question again? What's the value at?
What is the value of our acceleration when we go from this velocity, which would be 15 meters per second, down to 0?
I am so bad at this. I'm not entirely sure.
Which equation would we use? Alicia, do you know?
We use the same one.
Yeah, exactly. We can use the exact same equation. Let me actually go ahead and write it down. We have V, in this case V is V final, is equal to V naught, which is V initial, plus AT. We want to solve for A, right? So let's go ahead and say A is equal to V minus V naught over T. What is our V? What's our final velocity?
0.
0.
Oh, gotcha.
What is our initial velocity?
15.
15 meters per second. And what is our time? How long does the brake occur for?
1 second.
1 second. So our acceleration would be
Just negative
negative 15. And what are the units?
meters per second. Per second.
Did you just say meters per second per second?
Yeah.
Yeah, exactly. Or meters
Okay.
per second squared.
Yeah.
Meters per second, because it's 15 meters per second difference in 1 second. So then, what would be the average velocity of the car throughout the whole 10 seconds? You guys know how we would be able to calculate that?
Not off the top of my head. Can we still use that same equation? No. I mean, it'd be the final velocity minus the initial velocity divided by 10 seconds, right? Or can you not do that?
Well, for the whole motion, our final velocity would be... What would be our final velocity down here?
know.
It would be negative 4 meters per second, right? Because it's negative 2 meters per second squared for 2 seconds.
Okay.
So our final velocity is negative 4 meters per second. Our initial velocity is 0. So by your logic, the average velocity for the whole motion would be negative 2 meters per second.
That's not right.
I don't think that's right, because that would mean we'd end up somewhere down here. So we're not quite able to just use one simple equation to solve this, right?
Okay.
What do we need to do?
I don't. I don't know.
We're going to need to break this down step by step.
Okay, so do we need to break it down into like the chunks of
Yes.
change in velocity?
That's what I would recommend.
Okay.
And I would think more specifically, let's figure out how far did we travel? How far is this? What is this value here? And if we know this, then we know, if we were to draw a straight line, if I can draw a straight line, wouldn't the slope of that line just be our velocity, our average velocity?
Yes.
Or our average velocity is, I don't think it's in the formula sheet, but it's something that's quite simple. It's our total displacement divided by our total time. So this here is our total displacement here, however many meters, divided by our total time, which is 10 seconds. So how do we get our total displacement?
Could we use like the area under the velocity versus time graph?
Absolutely. So what would be our total displacement? Let's actually go ahead and break it down step by step. You said it was the area under the curve for the velocity versus time graph. So what is our displacement for the first, we'll call it step 1, 2, 3, and 4. 1, 2, 3, 4. What is delta x 1? How do we get the area here?
The integral.
Do we want...
Yeah, never. Go ahead.
Sam, I'm gonna ask you a completely honest question. Do you want to solve an integral?
I liked them when I took calc, but
because you could.
I don't. I'd rather not. Yes. No.
You'd rather not. And
Yeah.
Sure, you could solve this integral, but reality is it's a pretty simple integral, but like introducing the concept of an integral is just sort of like complicates the problem more than you need to. Let's dumb it down more. We're not going to worry about an integral.
Times space times height.
Exactly. It's geometry. It's a triangle. Half times base times height. So what's the base?
It's 2.5. Well, it's 5, but
5 seconds. Yep. So 2.5, and then the height.
I don't know what is the height. I don't understand what was our values.
What was our final velocity? 15 meters per second.
Okay, gotcha.
So delta x is equal to half times 5 times 15. Plug into a calculator. Math. It should be 37.5 meters. Is that right? Yep. So 37.5 meters is the total distance traveled in our first section up to here. So now for the second part, delta x2, how do we get our area under this curve here?
That's just 2 times 15.
Exactly.
30.
Exactly. 2 seconds times our 15 meters per second, 30 meters. What about this third part here?
7.5.
7.5.
Yeah.
So we have
Right.
1 second, 15. Yep. Half times base times height, we have 7.5. What about delta x4?
Negative. How many seconds? That's 2 seconds. Again, I'm not quite sure what the height, how we figure out the height for that. Though.
Wow.
What was that, Alicia?
It was -2. Oh, that's over.
The acceleration is -2 meters per second for 2 seconds. So what would be the final velocity?
2.
Oh,
Oh,
-1.
What was that?
-4.
-4, exactly. Yeah, sorry, your mic keeps like cutting out here and there, or it's like
Yeah, my mic is kind of bad.
it's like every time you start talking, it sounds like you just talk like this for like the first second and then it's fine. So maybe I'm going to request that you loudly say and then say whatever you're gonna say. So then the is muffled and then everything else is good. I don't know, we'll figure it out. It's just I might need to ask you to repeat things. But so yeah, height is -4. Our base is 2 seconds. So half times base times height.
Oh, just be -4 again.
Yep, -4 meters traveled. So all we do now is we want our average velocity, so we'll say v average. Is that the notation he uses? Does he use that at any point? It doesn't seem like he does, but
It's fine.
pretty
I
common notation. The bar across the top means average is equal to delta x total divided by delta t total. So our total displacement is 67, 75, 71 meters divided by our 10 seconds. So our average velocity is 7.1 meters per second. And it's a positive 7.1 meters per second in the x direction, but since it's 1D, we don't need to worry about that. Positive 7.1 meters per second is our average velocity. Does that make sense? You guys have any questions?
think that makes sense.
Yeah.
I mean, I'm sure it was.
Wait, go ahead. You guys you guys like interrupted each other, and like
Yeah.
the way Discord works is like it has like there's some sort of way where there's like some sort of a priority speaker in a channel, and so then when you have two people talking at once, it just like garbles everything, and then both people cut out. So go ahead, Sam.
I was just gonna say I'm fine for now, and I'll try to keep practicing. But like I know when I get on, like when I take the quiz or whatever, I'm just gonna forget everything. So
I mean, the best thing you can do is just practice.
Yeah, I know that's what I'm trying to do, but it's.
And Alicia, you want to say anything?
Yeah, this made a lot of sense actually. I was kind of struggling with the problem during class, but I think maybe I'll take an approach like this to it.
Mm-hmm. Yeah, I mean, an approach like this where you like draw everything out and you sort of like try to take everything step by step, it can be a little time consuming. So I'd recommend like only do it if you know you definitely have time to do it on a problem. But for the most part, I mean, there is no better way to actually truly understand everything going on than to break it down step by step and do something like this. And best way to do it is do that while you're practicing, and then get comfortable with the material, and then you'll be able to more smoothly go through it and maybe take shortcuts on the quizzes themselves. So let's go ahead and hop into one more quick example before we wrap up the session. We're going to have a 1 kilogram ball, and we're going to go ahead and throw it straight upward with an initial velocity of 20 meters per second at the top of a cliff. So we're going to go ahead and have a big old cliff. Do we want to name our cliff? We'll call him Jerry. We're going to go ahead and toss our ball upwards with an initial velocity of 20 meters per second at the top of Jerry. So it's going to go ahead and fly upwards. Initial velocity 20 meters per second. We want to know what's going to be the maximum height the ball reaches. And then also, what's going to be the velocity of the ball after 3 seconds? Let's use g is equal to 10 here, because it really simplifies this problem.
I kind of don't really remember what he was saying about free fall the other day. But, right, it would, so when the ball is thrown up, the velocity will slow down, right?
Mm-hmm.
Okay.
At what rate?
Yeah, so it really depends on also how high that ball goes, right?
Well, you should be able to understand it using the kinematic equations. You should be able to break it down.
Okay.
So let's think of it this way. So we have 5 kinematic variables for this 1D motion. We're going to have our displacement, delta x. We have our velocity, final. We have our velocity initial. We have acceleration. And we have time. If we have 3 of these 5, we can solve for the other 2 using our kinematic equations. What 3 do we know for this first part? How do we find the maximum height of the ball?
We know the initial velocity.
Exactly. We'll say it's plus 20.
Do we know the time? I don't think we know the time.
Nope, we don't know what the time is.
Do we know what the final No, we don't.
Why wouldn't we know?
I have no idea. I have no idea.
0, exactly. The final velocity is 0 because we're reaching the maximum height. So it's when the ball goes up, I mean, surely this makes sense. You toss a ball upward, you see it goes up, it reaches rest, and then it falls back down. And that's what's happening here. And then, so what else do we know?
It would be negative g, right?
Yep, exactly. In this case, negative 10. So, how do we solve for delta x? What equation do we use to solve for delta x? I'll give you a hint. There is one equation on your kinematics motion equation sheet that does not have time.
I don't know what equation that is. The final velocity.
What was
Go
that?
ahead, Alicia.
Oh, v squared minus v naught squared equals 2a the delta x.
Exactly. 2a delta x. V squared minus v naught squared is equal to 2a delta x. And so let's go ahead and solve for delta x. We know that v is 0, so it's So delta x is negative v naught squared over 2a. We plug in our values. Let's go ahead and pull up a calculator. We have negative 20 squared divided by 2 times negative 10. We reach a maximum height of 20 meters above. 20 meters above where we start. Does that make sense?
Kind of. I mean, when you have the equation, it makes sense, but like I guess I have trouble setting up the problem, which is why.
Remember what I said earlier? Get comfortable being uncomfortable. Stuff in physics, it sort of doesn't really make conceptual sense, or it's hard to understand conceptually. But like you just said, a literal exact quote, when we set up the equation, it made sense. The math checks out. And if you really want to think about it conceptually, if we were to solve for time, by the way, we would get 2 seconds. And in those 2 seconds, it starts at 20 meters per second, it ends at 0, so the average velocity is 10 meters per second upward, 10 meters per second upward for 2 seconds. It'll travel 20 meters up.
Okay.
So now, what would be the velocity of the ball after 3 seconds? See, we look at our 5 variables. What 3 variables do we know here?
We know the initial final velocity and the acceleration.
We don't know the final velocity. That's what we're trying to solve for.
Okay. Okay. And we know delta x, right? No, or just I guess not.
We don't know what delta x is.
Yeah, that's okay.
So like these kinds of problems, we have to break up into 2 parts, right? Like when it's going up and then when it's coming back down.
Do we need to break it into 2 separate parts? Because we absolutely could, but do we need to? Is our acceleration changing at any point?
Oh, no.
No, it's always 10 meters per second squared straight downward. So what formula do we have in our equation sheet that doesn't use delta x? That doesn't use x at all.
Oh, v equals v naught plus at.
Exactly. V is equal to v naught plus at. V is equal to v naught plus at. V naught is 20 plus negative 10, which is a, times t, which is 3 seconds. We get a final velocity of negative 10 meters per second. So after 3 seconds, it's traveling downward at negative 10 meters per second. Which makes sense, right? G is 10, so the speed decreases, or in this case, so the speed initially decreases, and then it starts becoming more and more negative at a rate of 10 meters per second. So how far below the top of the cliff would the ball be after 5 seconds? Which variables do we know in this case? See, delta x is what we want to know. Do we know the final velocity?
No.
No. Do we know the initial velocity?
Yes.
Plus 20. We know the acceleration. Negative 10. We know the time. 5 seconds.
Yeah.
So, what formula do we use that does not use final velocity?
E. I'm not sure.
What would be the first one, right?
X is equal to x naught plus v naught t plus half at squared. Exactly. So we go ahead and plug it in, and I'm going to say x and x naught. I'm going to ignore this and just say, put it as delta x. Let me actually go ahead and expand this a bit lower. Just a moment. Boom. So we have delta x is equal to v naught t plus half a t squared. We'll plug everything in. V naught, which is 20, times t, which is 5 seconds, plus half times negative 10 times 5 squared. We end after 5 seconds, negative 25 meters. So we end 25 meters below the top. And so the last problem, before we wrap up, if the cliff is 250 meters high, what time does the ball reach the bottom? Let's write down our 5 variables again. What do we want to find? Time. Delta x, we know it's negative 250. What's our final velocity?
No,
We don't frickin' know.
okay.
Our initial velocity, plus 20. What's our acceleration?
And negative 10.
Negative 10. What formula do we use that doesn't use our final velocity?
Is that the same one as before?
Yep, exactly.
Basically.
Same one as before. But in this case, we want to solve for time.
Gotcha.
It's ugly because we have the time and we have t squared and whatnot. So we have t and t squared. So let's go ahead and simplify this. Let's go ahead and remember after 5 seconds before, we were 25 meters below the top of the cliff, right?
Mhm.
So let's rewrite this, where in this case we're not going from the top of the cliff down to the bottom. We're starting at negative 25, so we only go down negative 225. Right?
Yeah.
We still don't care about what the final velocity is. And we still want to find time. Acceleration is still negative 10. What is our initial velocity?
I said it's 20 plus 20.
Wait, sorry, hold up. Let's think of this differently. Let's choose an example where the initial velocity is 0, so that we only have to worry about the half at squared. Where is the velocity 0?
At the very beginning? No, at the top.
At the top, exactly. So we're going to choose when velocity is 0, negative 10. We still want to find time. We don't care about the final velocity. How high did our ball reach?
Yeah.
20 meters, exactly. So we add 20 meters, so we're going down a total amount of 270 meters. Right? Does that make sense?
Yes.
So now we just plug in. So we have delta x is equal to v naught times time, but that's canceled out because v naught is 0. Is equal to half AT squared. So then T is equal to, we have 2 delta X over A square root, which is equal to, we have square root of 2 times negative 270 divided by negative 10. We get a time of we'll round it to 7.3 seconds. And that's after reaching the top. And so how long did it take to reach the top again?
What? 2 seconds? What would you say?
Exactly, 2 seconds. Why is it 2 seconds?
Because we threw the ball at 20 meters per second with the initial velocity at 20 meters per second.
Mm-hmm. And so why would it take 2 seconds to go from 20 meters per second to 0?
I don't know.
Because our acceleration is negative 10?
Exactly. Acceleration is 10. 20 divided by 10 is 0.
Okay.
You guys have any last questions about this?
I don't think the quiz problems probably won't be as complicated as that, right? For now? Or they probably will be.
I mean, if you think about it, this isn't too complicated because all you're doing for each problem is you write down what you know, what you don't know, and then you look at your equation sheet and you figure out what you need to solve it. And that's honestly how you should work. That's how you should approach pretty much every problem you'll see for this entire course. Write down what you know, or as I say, write down first of all what exactly is happening. So try to somewhat visualize it. Oh, me throw a ball off cliff. Roop, roop. And then think, okay, what do I know? What do I want to know? What do I need to find it? And with that, and then just worship the formula sheet, and you'll be fine, honestly. You won't need to worry about it too much. So, if there's no questions, I'm going to go ahead and wrap up the session right there. I want to thank you guys for popping by. Hopefully this helped out a bit.
Yeah, no, it did.
Good luck on your homework and your quiz tomorrow. And same time on Thursday, covering tomorrow's material. Maybe actually, honestly, I might push it back a little bit to 1:15 because I have my Physics 122 session from 12 to 1 right before it. And
yeah, no problem.
Well,
yeah, if you need to get like lunch or something.
I mean, the lunch isn't the problem. It's the fact that I go over time because I enjoy doing this and I spend too much time doing things. Like we've gone over almost like 10 minutes now.
Yeah.
Yeah.
Well, I really appreciate it.
Yeah.
Thanks, Dylan.
So I will say maybe 1:15, so that if I go over on Physics 122, I have time to like pee and get a drink of water and get ready for things. Because today I literally went from Physics 122 end session, swap over to this Discord, and then go. But
yeah, whatever you need. I mean, I don't have a job, so I can meet anytime. So whatever is best for your schedule.
Mm-hmm. All right. Well, thanks guys for popping through. Hopefully this helped out.
Yeah.
And I'll see you guys tomorrow in class.
All right. Thanks, Dylan.
All right. Bye.